In this session, we're going to look at our first two statistical tests, a test of a mean and a test of a proportion. These two tests are rather similar in form. They each ask the question, is my mean, or my proportion, equal to this particular value? The value that we're interested in will depend on the context of the problem. Before we jump in, let's quickly review the 5 steps of every statistical test. First, we look at the assumptions. Second, the hypotheses. Third, we'll need a test statistic. Fourth, we find the p-value that corresponds with that test statistic. And then finally, we draw our conclusion. We'll look at each of these in turn for each of our 2 tests for today. First, the test of a mean. Suppose we want to know if people adhere to a 40-hour work week. That is, we want to know if the mean number of hours people work is equal to 40. The 2004 General Social Survey asked, how many hours did you work last week? For 895 men, the sample mean was 45.3, with a sample standard deviation of 14.8. For 860 women, the sample mean was 39.1, with a sample standard deviation of 14.6. Why can't we just look at the sample statistics to answer the question of whether men and women work 40 hours a week on average? We only have a sample, not the entire population, and each time we draw a sample, we'll get a slightly different result. We have to take into account the variability in the sample to determine whether these results would be unusual if people actually did work 40 hours a week. To draw a conclusion about whether the population mean number of hours worked is 40 based on our sample, we can conduct a statistical test of a mean. First, we start with the assumptions. We have 3 assumptions for the test of a mean. First, the data have to have an interval or ratio level of measurement. Second, the data need to be obtained through randomization, that is, through random sampling or random assignment. And third, either the population needs to be approximately normal, or we need to have a large enough sample size, at least 30. Here, we've measured the number of hours that people have worked, which is a ratio measurement. The General Social Survey is based on a random sample of the U.S. adult population, and we have a large sample, so we don't need to worry about whether the population is normally distributed. The central limit theorem will help us out. Next, what will our hypotheses be? For a test of a mean, the null hypothesis will always be the population mean equals some value from the problem. We can call this null hypothesis value mu0. In this case, the null hypothesis for this example is that the population mean equals 40 versus the alternative hypothesis that the population mean does not equal 40. Here, we're doing a 2-sided test. People could work either more than 40 hours a week or less than 40 hours a week. In our statistical test, we're going to assume, for the sake of argument, that men and women really do work 40 hours a week on average. Then we'll look to see if the results from our sample would be surprising if that really were true. Third, we need a test statistic. Recall that a test statistic is a standardized measure of the difference between our data and what we were expecting under the null hypothesis. The test statistic for a mean looks like this. Let's call it t, and it's the difference between the sample mean and the null hypothesis value, and we're going to divide it by the standard error so that we get a standardized result. Recall that the standard error is the population's standard deviation sigma divided by the square root of n, the sample size. But we don't know the true population standard deviation, so we can use the sample standard deviation as an estimate. In our example, for the men, our test statistic t is 45.3, that's the sample mean, minus 40, that's the value from our null hypothesis, divided by 0.495, that's what you get for the standard error. And if we simplify that, we get 10.7 as our test statistic. For women, our test statistic t is the difference 39.1, that was the sample mean for women, minus 40, that was our null hypothesis value, and we divide by 0.495. So it happens that the standard error for men and women is the same in this example. When we simplify that, we get a test statistic for women of negative 1.8. Fourth, we want to find the p-value. The p-value is an indication of how unusual the results from this sample would be if men and women really did work 40 hours per week. The p-value is also the tail probability of the sampling distribution for the test statistic. What sampling distribution does our test statistic have? Well, since we used an estimate of the population standard deviation instead of the true population standard deviation, our test statistic has a t-distribution, and the number of degrees of freedom is 1 less than the sample size. So in our example, when we compare the test statistics for men and women with the appropriate t-distributions, we get a p-value of less than 0.1% for men and a p-value of about 7.2% for women. How can we interpret these p-values? Well, if men and women really did work 40 hours per week, then the sample means for most studies would be pretty close to 40 hours. But if they really did work 40 hours per week, in about 7% of studies, we would find the average number of hours that women worked in our sample would be more than an hour different from 40 hours. So that is to say, the sample mean would be less than 39 hours or more than 41 hours in about 7% of the studies. And for men, in less than 0.1% of studies, we would find the average number of hours that men worked was more than 5 hours different than 40 hours. That is, less than 34.7 hours or greater than 45.3 hours. Finally, based on these p-values, we can draw our conclusions. If p is less than 0.05, then we call the results unusual. For women, the p-value was 0.07, so it wouldn't be all that unusual to see a sample mean of 39.1 if the women really did work 40 hours per week on average. So we conclude that women could very well work 40 hours per week, because we didn't find anything unusual in our sample. For men, though, the p-value was less than 0.001. So if men only worked 40 hours per week, it would be very unusual to have a sample mean of 45.3. So we start to think that men must work more than 40 hours per week, since the results from this sample would be pretty unusual if they only worked 40 hours per week. Now suppose we're interested in a proportion instead of a mean. Let's think about this scenario. Astrology is the study of how the patterns of constellations are connected with events here on Earth. There have been many studies that investigate evidence for these conclusions. In one such study, horoscopes were prepared for 116 adults, and these adults also took a personality survey. Then astrologers were given a horoscope and 3 personality surveys, one for the same person as the horoscope, and then 2 other random surveys. The astrologer had to match the horoscope with the correct personality survey based on astrology. They did this 116 times. Now, anyone could guess correctly about 1/3 of the time, but the astrologers claimed that they could do better than 1/3 correct, because they believed that the astrology was helping them find the correct answers. Let's look in detail about how to test their claims statistically. In this study, the population includes all the astrologers' possible matches. This is a hypothetical population of all the matches they could possibly make. And our parameter of interest, that is to say the numerical summary of that population, is the proportion of those matches that are correct. So we want to test a population proportion. As always, we first start with the assumptions for the test of a proportion. There are 3. First, the variable has to be nominal. Second, the data have to be obtained using randomization, that is, a random sample or some kind of randomized experiment. And third, the sample size needs to be large enough that the sample proportion is approximately normal. That is to say that our expected successes, that's our sample size times our population proportion, and our expected failures, our sample size times 1 minus our population proportion, both need to be at least 15. In the example with the astrologers, each observation is either correct or incorrect, so we have a nominal variable. The data are also obtained by randomization, since we matched up the correct horoscope with 2 randomly selected horoscopes. In this example, what are the expected number of successes and failures? Well, if the null hypothesis is true, that is to say, if the astrologers are only guessing, we would expect them to get 1/3 of the answers correct. 1/3 of 116 chances is about 39. And if they get 39 correct, then they must get 77 incorrect. So that's what we would expect if they really were just guessing. The expected number of failures and successes in this case are each more than 15, so we meet this final assumption and we can proceed with the test. Next, we need to set up our hypotheses. We want to know if the astrologers are just guessing, but we need to convert this goal into statistical terms. If the astrologers are just guessing, then they'll probably get close to 1/3 of the matches correct. So we want to know if the population proportion of correct matches is 1/3. Or in symbols, the null hypothesis is that the population proportion equals some special null hypothesis value, which in this case is 1/3. P equals 1/3 is our null hypothesis. What's the alternative hypothesis? Well, the alternative hypothesis is an opposite of the null hypothesis. We could choose a two-tailed hypothesis, that is, the population proportion doesn't equal our special value of 1/3, which would allow the astrologers to get more than a third of the answers correct or less than a third of the answers correct. But the astrologers don't just claim that their success probability is different than 1/3. They claim that it's better than 1/3. So let's use a one-tailed alternative hypothesis. That is, our alternative hypothesis for this test will be that the population proportion is greater than 1/3. Third, we need our test statistic to measure how different the results from this study were from what we were expecting under the null hypothesis. The test statistic for a proportion looks like this. We take the difference between our estimated proportion and the proportion from our null hypothesis, and we divide by the standard error. Now remember that the standard error for a proportion is the square root of p times 1 minus p divided by n. What kind of p are we going to use here? Well, we're not going to use the estimated proportion like we use the estimated standard deviation in the test for the mean. Instead, let's use the proportion from our null hypothesis. That's why I wrote SE subscript 0 in the equation for this test statistic. So for our test statistic of a proportion, we'll take our estimated value of the proportion from our sample, and we'll subtract the value from the null hypothesis, and then we'll divide by the standard error using that value of the null hypothesis. So that's the square root of p0 times 1 minus p0 divided by n. So in this case, for the astrologers, they got 40 out of 116 of their chances correct. So the sample proportion is 40 out of 116, which is about 34% correct. And our standard error is going to be based on our null hypothesis value of 1/3. So we'll take the square root of 1/3 times 1 minus 1/3, which is 2/3, and divide by 116, which was our sample size. That comes out to be 0.0438. So for our test statistic, we take 34% and subtract 33% and divide by 0.0438, and that gives us 0.26. Now we can use this test statistic and the sampling distribution to answer the big question, namely to find out how often you would observe this test statistic among a bunch of similar studies if the null hypothesis really were true. That is to say, how unusual are the results from this study. For the test of a proportion, the test statistic has an approximately standard normal distribution. So we'll take our test statistic and look up the probability from that a standard normally distributed variable is greater than the value of our test statistic, 0.26 in this case. This is for a one-tailed test. We look up the value greater than 0.26 because our alternative hypothesis said that the population proportion p was greater than 1/3. If we were doing a two-tailed test, we would have to look up both tails and add them together. So for our astrologers, our p-value is 0.4. Note that this is the p-value of the statistical test, not the population proportion and not the sample proportion. When you're working with a test of a proportion, it's really important to keep all of these p's separate. There are lots of different p's and you have to keep them separate in your mind. In this case, we're looking at the p-value, and that is 40%. This means that if the null hypothesis is true, that the population proportion of correct matches is 1/3, meaning that the astrologers are really only guessing, then in 40% of studies like this one, the astrologers would have at least as good a track record of correct guesses as they did here, that is, getting 34% correct. Let me say that again. If the astrologers really are guessing, then in 40% of studies like this one, they would get at least 34% of them correct. Finally, we'll draw our conclusion. Getting 34% out of 116 matches correct isn't all that surprising, since the p-value is pretty high. So we don't really have much evidence to suggest that the astrologers are doing any better than guessing.